principal investigator at the Conjugate Basin Tectonics and Hydrocarbon Research Consortium. You will hear more about him during the introduction. So let's get started. So our agenda is very strictly business today. We'll have the welcome remarks shortly, and then we'll have safety moment. We will have Mr. John Bosco, Fellow of NAPE, who is the NAPE president, to give opening remarks on behalf of the association. Then we'll have the chairman's remarks, and he will also introduce the speaker. Then we'll have the presentation from Professor Mann. And then there will be a recap by the chairman. Please note, this is a webinar style event, so we have a Q&A section. So look for it on your Zoom panel and just put in your question there, because we will have a Q&A session, 15 minutes. And we'll take some very important announcements, a very short one. We'll have closing remarks and vote of thanks. So let me introduce NAPE, North America chapter, to those of you who might not know us well. We are a community of professionals that cut across not just the petroleum industry, across the energy industry and beyond. This chapter is North America chapter. And NAPE is the largest professional association of energy-related disciplines, not just in Nigeria, but also in Africa. Our members include geologists, geophysicists. We have CEOs, managers, consultants, students, and academia. So let's get on to business with the safety moment. We'll have Dr. Chuma Onwumelu, who will give us a short safety moment. Chuma, I have your screen on. If you want.
Okay. Perfect. Can everyone hear me?
Yes.
Okay, perfect. So, hi everyone.
Yes.
Okay. I would like to take a few minutes for a safety moment on a topic that impacts most of us daily, and that's on economics and awareness during virtual meetings, like this one which we are in now. So as our work environment shifts more and more into digital space, small things like how we sit and how we interact with our devices can have big effects on our well-being. Let's walk through a few key tips to stay safe and be productive during virtual work. Number one is sitting properly. You start by checking your posture, make sure that your monitor is at eye level and that your back is supported. Slouching and looking down at a laptop screen for a long periods of time can lead to neck pain and even a back pain. So if your laptop is like much lower than your eye level, you try using something to prop it up. You can also try to use a separate keyboard or mouse to improve your alignment. Then number two is avoiding distractions. We often think that we can multitask during virtual meetings, maybe check our emails or even respond to messages. But the truth is that multitasking reduces our productivity and increases errors. So staying focused not only helps you to contribute better, but also it minimizes the chance of missing important information or even making mistakes. Number three is taking breaks. A common issue when working virtually is eye strain. So a good rule of thumb is to, is the 20-20-20 rule. So for every 20 minutes, look at something 20 feet away, at least about 20 seconds. This will help you reset your eyes and also it will reduce fatigue. And also don't forget to, get up, stretch, walk around, just between meetings because it makes a difference. And then number four, be aware of your surroundings. Always mute yourself if you're in a noisy space. try to use headphones to reduce background noises. And because it will reduce or it will improve the audio quality for yourself and also other people in the meeting. And also be very aware of what you have in your background, especially if you're working in a shared or a public space. Then number 5 is don't zoom and drive. This may seem very obvious, but it's worth mentioning because we do that most of the time. So it's never good to attend meetings while we're driving, even if it's just listening, because it's going to divide your attention and also it increases risk. So if you're on the move, if you're traveling or doing something, it's safer to let your team know and also try to join the meeting when you reach your destination. One last important point is always to double check your screen before sharing. Just make sure there are no sensitive tabs or notifications that are visible, because all these small steps can protect both you and your organization. So to give a quick recap, number 1 is take care of your posture, avoid multitasking, give your eyes breaks, stay aware of your surrounding, and never zoom and drive. And lastly, be mindful when sharing your screen. These simple actions can help you stay healthier, more focused, and safer, both during meetings and throughout your day. Thanks for taking time to think about your safety.
Thank you, Dr. Chirma. That was short, apt, and timely. We'll move on to the next item. We're gonna be inviting the president of NAPE for his opening remarks. I will be inviting the esteemed NAPE fellow, Mr. John Bosco Uche, FNAPE.
Good day, Manajimoke Akinpelu, and the chapter coordinator for North America, the entire ISCO members, and our guest speaker, and every other one that are dialed in. I see the president-elect is also on the call. I know this time, especially for myself and the PE, it's usually not the best, but we are committed to continue to stay connected with the North America chapter because we value every single thing you've been doing. You are the eye of NAPE at the global level. And most of the progress we've made, our connect with AAPG and other external organizations in the US, you keep doing it excellently well. And today is not an exception, right? I mean, having been able to secure well thought out professor, Professor Paul Mann, I think he's another key one, and there's no way we wouldn't dial in to be able to key in and also listen to him. In fact, actually, when I looked at the topic, it's one of the things or topic that NAPE has been advocating strongly in Nigeria, in the Niger Delta. As we know, Niger Delta is quite prolific in the Deepwater, but we do believe as NAPE that there are a lot of opportunities still out there, which can be categorized as frontier as well in the Niger Delta, in the older rocks. And therefore, today is quite timely that NAPE is providing the platform for the folks that are dialed in to listen to Prof. And that's why we're here. So we really want to welcome you and continue to provide the platform for knowledge sharing. And that's what we do quite well and we'll continue to do so. So on that note, I want to say thank you so much, our North America chapter executive committee members and members for making us proud and continue to keep the light shining as our ideas continue to find oil and gas in a sustainable manner. So with that, I will yield the floor back to you, Joke.
Thank you, Mr. P. Well said. We appreciate your time staying up late in Lagos. So we'll move on to the chairman's remarks. He will say a few words and then introduce the speaker for today. The chairman for the talk today is Mr. Akpofure Isiapere. He is a Geoscience Operations and Geoinformation Manager at Total Energies for Americas. Mr. Isiapere, in his 2 decades experience working at Total Energies, has taken on multiple technical and managerial roles, spanning different petroleum regions and basins in diverse environments of the position. He has also made significant contributions to multiple ED&P projects in the Americas, Europe, and Africa. I'll call on Mr. Isiapere now for his remarks.
Many thanks, Jumoke Akinpelu, for such an introduction. Much appreciated. Thanks again for welcoming me in this capacity for this technical session. So I still remember not too long ago being present at the initial conception of North American chapter. So well done, Ademola and the rest of the team for where we are today. And I believe that it really does make me feel very confident of the future of the chapter. And thanks as well to Mr. John Busco Uche and the rest of the team back home for all your continuous support despite the timing of our technical event. So thanks a lot for your continuous support. So on the subject for today, so as we all know, to extend the frontiers of deepwater exploration, the global industry has advanced in seismic acquisition, drilling, development technologies, and moving from shallow waters to even ultra deep waters and high temperature and pressure reservoirs that were previously unreachable a few decades ago. So these advancements are primarily driven, of course, by in-depth understanding of the regional basin evolution, as well as a good synthesis, of course, of seismic as well as well data, which are essential for helping us to comprehend the petroleum geology of sedimentary systems and helping us to unlock those hydrocarbon potentials in these different geological basins. As all explorationists in NAPE, we are at the forefront of discovering these new opportunities, and I'm thus eager really to listen and to learn from our renowned speaker on this important topic, which of course plays a significant role in securing today the energy that we need for the world needs for tomorrow. I'm confident that the insights that Paul Mann will share today will be valuable to all of us in our venture for exploration. So allow me to introduce our speaker for today, Professor Paul Mann, who is a distinguished geologist recognized for his extensive contributions to tectonics, basin analysis, and petroleum geology. He earned his Bachelor of Arts degree in geology from the Oberlin College in 1978 and completed his PhD at the State University of New York at Albany in 1983. Currently, he serves as the Robert E. Sheriff Endowed Professor of Geology at the Department of Earth and Atmospheric Sciences at the University of Houston, Texas. He's the director of the Conjugate Basins Tectonics and Hydrocarbons Project, CBTH, which is a project sponsored by many IOCs, including TotalEnergies as an active sponsor. He leads a comprehensive regional synthesis of seismic and well data to assess hydrocarbon potential across diverse geological basins, including the Caribbean, Northern South America, the US and Mexico offshore, and some reef-fed passive margins in Central Americas, East North America, South America, Western Europe, and of course, West Africa. His work has significantly advanced the understanding of petroleum systems and basin evolution. And in terms of accomplishment, he has held previous prestigious positions at multiple institutions, including serving as a senior research scientist and lecturer at the University of Texas at Austin from 1983 to 2011. His accolades include the Philbetta Kappa Honor, the SUNY Albany Presidential Award for Outstanding Doctoral Dissertation, and fellowships from esteemed institutions such as the French Academy of Science and the Geological Society of America. So he has served as an associate editor for multiple scientific journals, including Geology Society of America Bulletin and the Marine and Petroleum Geology. And he has developed and continues to teach graduate level courses on petroleum geology, basin analysis and technologies, and mentoring numerous students who have gone to make significant contributions in academia and industry. And in fact, he continues to further research on multiple geoscience subjects with different PhD students at the University of Houston. Actually, a couple of them are currently in my office. So I encourage you all to participate actively in these discussions and make use of the chat bar, as Jumoke mentioned. So without much further ado, welcome Professor Mann.
Okay, thank you for having me. And let me just share my screen.
So while Dr. Mann is pulling up his screen, I want to recognize the presence of the President-elect of NAPE. This is Olajumoke Ajayi, FNAPE. Thank you for joining us.
Okay, can everyone see my screen?
Yes.
Okay. So thank you for that introduction. I really appreciate it. And also thank you, Total Energies, for supporting this project for a long time, many years. So we have now we have 5 sponsors of our project that include Total Energies. So the outline today is to go over rifted passive margins. That's going to be our main focus. And this is where the deep water exploration is happening in the deep water areas of rifted passive margin. But there are several different types, non-volcanic, volcanic, and then sort of combinations. So I'll go over that. But also pointing out the importance of rifted passive margins to recent discoveries such as Guyana, southeastern Brazil, Namibia, where this is sort of the forefront of exploration today. So, and also I'll point out some of the differences between a rifted passive margin and a transform margin or a strike slip margin. They're very different, which is important for understanding the hydrocarbons. And after we kind of get through all this sort of terminology, I'm going to talk about certain areas, Guyana, Equatorial Brazil, West Africa, Namibia, and other places, just to kind of show you, these are all areas which are big discovery areas. What is it about those areas that we can apply to maybe less known areas, like, for example, the deep water of the Niger Delta? So before I go, though, let me just start with some definitions. Rifted conjugate margins. So conjugate margins mean they originally were together. It's like conjugal, like they were originally married margins. They were together. Once a margin rifts, it becomes a passive margin. The boundary between the rifted continental crust and the ocean crust is called we call it the continent-ocean boundary. Other people have other names for it, but we find COB to be a very succinct way to express that. The oceanic crust here, which is thinner, 6 to 8 kilometers. And then over on the other conjugate margin, we have the other COB, conjugate ocean boundary. So this is the Black Sea, and it makes a nice slide because it's a relatively small ocean basin. But before I get started with all the different areas we're going to talk about, I want to just point out that most of this work was done by persons other than myself, and they're listed here. These are former students, current students. Kenneth Shipper is now down at Total Energies. That should be Daniel Maya. I didn't do that correctly. Kenneth Shipper is also one of our students. Jose Gorosabal is our postdoc. Josh Miller is also down at Total Energies. Some of these students have graduated. Some are still with us. Everyone knows Jamoki. Andy Pepper is really a key collaborator who's one of the world's experts on source rocks. And we spend a lot of time collaborating with Andy. And then Jean-Marie Legel, some of you probably know, runs this company called Explore, which makes the Excalibur software that I'll be talking about. And I mentioned there's actually Chevron is one of our sponsors. It's not shown on this slide, but these are our 5 sponsors. So where are the rifted passive margins located? Most of them are in the Atlantic. So that's the area that we're going to be talking about today, from South America, Africa conjugate margins, Northwest Africa, Eastern US, and then we won't say much about the North Atlantic, but so we're going to be more focused on the Central and South Atlantic. But there are other areas of passive margins: the Indian Ocean, Australia, the Antarctic, which is closed for exploration, but the Arctic, which is controlled by Russia, Canada, Greenland, and Canada, USA, and Russia, is this vast area up here, which is not actively being explored, but was several years ago. So, and notice the red areas on here. These are the active margins. So these are active subduction margins. These stars represent large earthquakes. So you can see these are areas where there's a destructive force going on, not making such a good environment for hydrocarbons as these passive margins where rocks are left to sort of settle in and not be disturbed by later deformation. So the Tethys is the former ocean, now this part of Asia, where all of those basins were destroyed and now have been uplifted as mountain belts. So our area, though, the Atlantic, is where Pangaea broke up. So Africa separated from South America and North America. So we're going to be looking at those particular rifted margins. So what about hydrocarbons? Like I said, most hydrocarbons are found in rifted passive margins because they're tranquil environments that are not disturbed by later tectonic events. So if we look at the number of giants, and this was from an old diagram about 15 years ago, you can see that over a third of all the giant fields are on passive margins, or actually about 60% are either on passive margins or continental rifts. So this is the sort of the sweet spot of tectonic settings for finding oil. Of course, there is oil in other settings, collisional margins, strike slip margin, subduction margin, but you can see how this trails off because these active areas are not efficient at preserving hydrocarbons. They tend to destroy basins at a pretty fast rate. So one of the major trends over the past 100 years or so is moving from on-land exploration. These are 1.4 million oil and gas wells that have been drilled in the state of Texas to offshore areas, which are not shown here in the Gulf of Mexico. But this trend has happened everywhere. Texas, the Gulf of Mexico, Brazil, all these countries have moved from on land to coastal to deep water. So like I said earlier, the main frontier now is this very deep water area out here, greater than 2,000 meters of water. If we look at recent discoveries, and these are all the giants compiled by Dolson et al. 2021, but you can see these sort of yellow boxes. So these would be clastic hosted giant oil fields. A lot of these are now happening in the deep water area, both Brazil, West Africa, this doesn't include Namibia, Northwest Africa over here, Guyana, Gulf of Mexico. So you can see there's a lot of, this is where the big fields are being currently discovered. If you look at this trend also compiled by Dolson, you see the depth of wells drilled by year. So starting by 1860, everything is on land. And then by about 1970s, 80s, we start getting into deeper and deeper water. Now this is down to about 3 kilometers. So again, it's this trend from on land to deep water offshore. So one of the major differences in rifted margins is whether they're non-volcanic or volcanic. So on this map, the volcanic margins are shown in this red color. So you can see East Coast of the US. This is actually not correct. We think the Northwest Africa is now a non-volcanic margin, but the green colors would be the non-volcanic margin. So this would include most of Brazil, Guyana, which is too small to be shown on here. And I'll talk about how Guyana changes very rapidly to the Demerara over a very short interval. And then we get down into the southern part of the South Atlantic, where we have Argentina, and this area is all a volcanic margin, as well as Namibia and South Africa. So you can see there's sort of an alternation. Usually, volcanic margins are opposed to each other, or non-volcanic are opposed. We're still puzzling over why Northwest Africa is non-volcanic, and yet Eastern North America is volcanic. And all these black dots on here represent the giant fields. So you can see there's sort of a spatial correlation of giant fields to non-volcanic margins. But we'll show in a little bit how discoveries are now happening in the volcanic margins, like, for example, Namibia, possibly Uruguay. So this could be opening a whole new frontier. One point I'd like to make about volcanic margins is prior to the rifting and the breakup of Pangaea, we have these huge plume effects. And this is the Piranha Entedeca lip or large igneous province, which is kind of down in this region, which includes Campos Santos in southeastern Brazil. But my main point is that sometimes you can have a volcanic event and then you can progress into a non-volcanic margin, such as I'll talk about in the Campos Basin. So that this forms the basement, but it's over by the time the rifting occurs in this area. So it's, you can see there's a lot of complexity in sort of the history of these events. So what do these margins look like in cross section? So this would be a non-volcanic margin. And notice the continental crust here is shown by this red color. This black would be the mantle. Ocean crust is out here, but you can see that the space that's opened up during the rifting process has filled with sediments. So there would be some volcanism going on as there is on any rifted margin, but not to the point of a volcanic margin. So if we come down here to the volcanic margin, you see the same general profile, but here all the space available was filled by volcanics known as seaward dipping reflectors, or SDRs, because they form these, some people call lava deltas, that just fill in every available space during the rifting process. So you can see these are very different mechanisms, very different outcome in terms of the lithologies that you would encounter. So one of our views is identifying what we call marginal rifts. So the marginal rift is the last big rift before you get to ocean crust. And some of you who work in the Gulf of Mexico are familiar with the step-up fault, where you step up from rifted continent into higher standing ocean crust. So we see this. This would be the Gulf of Mexico. This would be the marginal rift. The step-up fault would be this feature here. Notice the marginal rift is full of salt and sediment. These are not volcanic rocks. There could be some volcanism present, but not in large quantities. But when we come down to Namibia, you can see that the SDRs have completely filled this area in here. But nevertheless, we have a hydrocarbon system perched on top of the SDRs. So this would be the Venus submarine fan, which is a large amplitude anomaly, which was been the site of a major discovery. There's also some other fields up dip here. So you can see very different settings. Here we have rifts filled with sediments, diapurism, salt, lots of sediments on top. Here we have basically a volcanic basement that's overlain by these hydrocarbon-bearing rocks. So back to the Black Sea, just to do a little bit more with the terminology. A term you'll hear a lot is necking zone. So the necking zone refers to the distance between full thickness continental crust, which could be 40, 30, 50 kilometers over here, to the thinned out continental crust, which could get down to 5 kilometers out here in a non-volcanic margin. So the necking zone, you can see the necking zone here, you can see it over here, but it's really important because a lot of the hydrocarbon activity is going to be within the necking zone, some of which is in very deep water. This could be 2 or 3 kilometers deep. So I mentioned the term marginal rift, which is a term that we use. Other people have other names. Mark Rowan calls it the outer trough. Jim Pendel calls it the outer marginal trough. But it's all means the same thing. It's the last rift you see before you get to ocean crust. So this, on this diagram, you can see the rifting is happening, and at some point the seafloor erupts. There is intruded in this space that becomes available because of all the extension. So notice the seafloor is standing high. So we have the step-up fault on both sides. And notice this feature here shown filled with salt. So this would be the marginal rift starting out as a single rift right down the center of the basin. And then eventually that crust gets so thin, the seafloor, the oceanic crust can come up and you start a spreading system, which is going to separate the two marginal basins, which originally started out as one basin. So they're identical twins. One goes one direction, the other goes the other direction. So I mentioned the step-up fault. This would be the northwestern Gulf of Mexico near the Perdido. So you can see this thrust system here represents the step-up fault separating ocean crust over here from the marginal rift, which here has been inverted and folded as a result of all this gravitational downslope movement. But one of the things we'll talk about is we never see salt deposit on ocean crust. That's an axiom that I think is holding pretty strong over the years. You do see salt expelled onto ocean crust. Like here, for example, you've got salt that ramped up and now it's out on top of ocean crust. But this is not depositional. This happened as a result of downslope gravitational movements. So keep this model in mind as we go on to the Red Sea, which is a good example of this happening today. The Red Sea started rifting about 15 or 20 million years ago, and it has a lot of properties that we see in these kind of older Atlantic rifted margins. So some of you may remember these models from years ago. The simple shear model, this lower one, and the pure shear model for rifting. So the simple shear model has this low angle detachment fault, very asymmetrical. So you have sort of a stretching happening along this low angle fault. And you can see the two conjugates would have very different geology once they separate. But the other alternative model is the pure shear rifting. So in this model, everything is symmetrical. You have mantle rising up. You're going to eventually break your marginal rifts into two, and you're going to end up with largely symmetry on both sides, including the width of the rifted zone. So if we look at the Red Sea today, it's a good example of this, where we have this seam that runs right down the center of the basin. This is the marginal rift forming with ocean crust happening down in the southern Red Sea here. So ocean crust is actually starting to separate the marginal rifts down in the south. In the north, it's just a single marginal rift down the middle of the basin, which will eventually break as it's done down here, and you'll form ocean crust that separate the two halves. You can see these are marked by these deeps that run up through here. Down here, you can actually see some magnetic anomalies forming. So some of the things that are characteristic of the Red Sea that you see in other older systems in the Atlantic are the normal faults are all dipping seaward. So your spreading center, will eventually form out in this area. If we were to come over to the Saudi side, you see the same thing with all the normal faults dipping seaward. So these lines here, A, B, C, represent these different short lines. So the other thing of interest, though, is notice up in the north, so this would be A, B, C, you haven't gotten to ocean crust yet. So what you see is volcanic activity. You see this tilting as the mantle's rising up. And notice the salt. The salt is somewhat fault control, but largely it's like the Gulf of Mexico. It's more of like a big sag deposit. Okay, if we come south down to down here, you see the salt is sort of spilled out. It's gotten a lot thicker because the seawater is entering from the south. And you can see that if we came over a little further, this would be ocean crust here. So now we're starting to separate the salt into two halves. And this is characteristic of all these salt basins, that the salt formed originally and then it gets broken into two parts by the spreading oceanic crust. So if we go to the Gulf of Mexico and try to apply some of this information, this would be the marginal rift. This is a line across the northeastern GOM here. And you can see up here, there's a little rift with salt coming out of it. And if you go over to the other half, which would be down in this area, you see salt in a marginal rift, pretty much symmetrical. And out in the middle, you see the spreading center. This is the old abandoned late Jurassic spreading center. It's got an axial volcano sticking out. It's a slow spreading ridge. So we have marginal rifts on both sides of the Gulf. Some of you, if you follow the literature, Lundin et al. Just published a paper where they say the entire Gulf of Mexico is one big volcanic margin from top to bottom. And my feeling is that maybe back here near Florida, this would be the middle ground arc, maybe there's an older SDR section, but I find it a little hard to believe that this entire area is volcanic margin. Why? Because we see there are evaporites out here in the marginal rift, and this is full of sediment. So it's kind of a difference in, how different people see different things. We see all of this as sedimentary in the marginal rift. And you can see some dipping reflectors here, which might reflect some older volcanic event, like I showed for the Piranha lip in Brazil. So it might have preceded the rifting, but volcanism did not accompany the actual breakage and formation of the ocean crust. So now just to jump southward to the Campos Basin, and this has a lot of relevance for deepwater exploration because a lot of time and effort has been put in to try to see, is this basin productive? Could this basin contain hydrocarbons? We're in about several kilometers of water. It's maybe 2 or 3 kilometers of water. We've got a salt layer. We've got the ocean crust out here. Notice a step-up fault here. And notice salt wasn't deposited in ocean crust, but it has been expelled on top of the ocean crust. And notice this very deep little basin here. This would be the marginal rift. If we come over to the Kwanza Basin in West Africa, you see almost exactly the same thing. There's the step-up fault. This is the deep part of the marginal rift. This whole area is rifted, just as this part is in here. And then this sort of steps up here in Brazil. This is called the external high. Over here, this is just the continental margin. But notice that steeper dipping this margin, all the salt is sort of cascaded down and piled up, whereas in Brazil, it's a little bit flatter and the salt is more diapiric. So these are the conjugates. So originally these two were together, before the ocean crossed. This rift and this rift were right. They formed one rift, and now the ocean crust has come up between them. Okay, so these are the conjugates, and back to exploration though. This is work by Ruth Beltran, who's one of our students. But you can see it's a subsalt play where you've got coquina limestones and other things that are beneath the salt, very similar to the external high where most of the discoveries have been made. But this is the value of trying to figure out, could a hydrocarbon system exist out in this deeper water area as it does sort of upslope from here. But just to show you some of her work and what she's located, you can see the rifting process has left these higher standing blocks, which have coquina. Some of these have been tested by wells. So these are high quality reservoir rocks. You can see the fault controlled rifts. This is sort of a sag sequence in here. And then the salt would be this big layer across the top. So keeping that in mind is sort of a non-volcanic margin. Now we're going to go over to Namibia. And again, I've showed this slide earlier, but you can see the SDRs have filled everything during the rifting process. But they've also produced sort of a platform-like structure for the deposition of these really high quality sort of Aptian, Albian source rocks in here, and their reservoirs are up dip and stratigraphic traps along this high here. Same feature over here. There's some downslope gravitational movement, but you can see, this really bright signature of the source rocks right above the SDRs. So we're looking now down. We're down in this area. So this would be the volcanic margin in Namibia, and this would be the South Brazil, Argentina volcanic margin. But one thing we found, we're doing a study, Daniel Maya is doing a study of Uruguay, Deepwater, and one thing that was interesting was, if you look at this line off the Rio de la Plata, you can see normal faults dipping seaward. So that would indicate non-volcanic, and you don't see any SDRs. But then what happens? The normal faults all reverse their throw. Now they're dipping landward. And that's always been a signature of volcanic margins. So we think that Uruguay may have started as a non-volcanic margin. And in that situation, you have seaward dipping faults, and everything's kind of tilted down as the mantle is depressed. But then during this phase here, you have an active mantle, a volcanic margin starts up, and that seems to be the trigger for the normal faults dipping in the opposite direction. So there could be sort of a complex history of non-volcanic, volcanic, or maybe in the Gulf of Mexico, it went from volcanic to non-volcanic. But here's just an image showing the SDRs. They're the last thing that happened here during the rifting process. So they're right along the edge of the oceanic crust. Okay, so I mentioned strike slip faults, and those are important in the equatorial Atlantic. So this would include Brazil, this part of sort of equatorial Africa that includes Nigeria. So what are the differences with those margins? If we look at a place like Iberia, Iberia is an orthogonally rifted margin. It's really thinned out, and you can see what we call the taper, right? Notice how this is very tapered. But if you come down to Ghana, which would be down here, it's at a very abrupt vertical fault between the continental crust, this heavy black line, and the ocean crust. So that represents a transform fault or a fossil transform fault that formed during the early opening. So this area extension is quite different, and we'll see these are mainly pull apart basins and little steps in these strike slip faults. So just to show that more graphically, these are reconstructions from different people. David Castro in Brazil has shown that, you know, the geometry of these small ocean basins are basically pull apart basins like you would see in the Gulf of California, for example. So these allow water to sort of seep in, and this is very important for hydrocarbons because you get very high quality source rocks in these sort of restricted environments. And I'll go over that in a minute. But again, you know, your ocean is open from the south. Seawater is getting in. The evaporites are kind of down in this area. They're sort of dissipating as you go north. And now you're breaking this transform segment here, and you're allowing that seawater to form the basis for very organic rich source rocks in this region. So this would be the equatorial margin of Brazil. So now just to zoom in on sort of more specific studies that have been going on with our group. So we've covered this, you know, is it volcanic, non-volcanic? I think we can recognize that pretty easily. Is it orthogonal versus oblique? We've done that. Where's the COB? So we use gravity, magnetics, and other methods to try to get at that. So that would be this white line here, and over here would be this white line here. So you can see that in South America, it's quite wide, the continental margin. It's somewhat narrow in parts of West Africa. Is there a marginal rift? So that's something what I showed you an example of that from Campos, which would be in here. How thick is the continental crust? So that gets into this idea of the necking zone. And the necking zone can vary widely. It can be quite extremely thin, or it can be thick. You know, I think it depends a lot on the original rock that's being extended. Are the source rocks syn-rift? Are they in-grabens? Or are they post-rift? And I'll show you an example of that in a minute. What is the overburden? So overburden is important in places like Uruguay. You've got the Rio de la Plata dumping sediment on this, pushing the Cretaceous source rocks down deep. You know, so some people prefer Pelotas, which has less sediment cover. So there's that issue of overburden. Is there salt or no salt? Well, there's salt pretty much all the way up the coast. It sort of peters out up by Equatorial Guinea over here and up in sort of this part of Brazil. And then what are the previous wells revealing? So we're compiling all these wells. You can see these green dots here are oil producing wells. You got yellow oil and gas, and then gas is red. So you can see these trends coming up here. Kind of peters out a little bit over the equatorial Atlantic and in places over here in West Africa. So the question is whether these trends are just reflect under exploration or whether they're true, whether they're real or not. So I mentioned basin modeling, and this is where our project is headed. we can do all this mapping, but what we want to do is put all of that information into a basin model, which is predictive, which shows where the trends are. We know what the source rocks are, we know how old they are, we know how deeply buried they are, we know their properties. So we can be very quantitative using this type of software. This is the Excalibur software from this company, Explore Lab. I mentioned Legal, who's our collaborator who created this software. But there's a lot of parameters that go into this, and I'll show you some examples of some of the inputs. So to do that, I was going to start with Guyana. So Guyana is a project we've been working on for several years now, and it's an interesting place in that it has a twofold rift history. It has an older Jurassic, sort of earliest Cretaceous rifting, and then it has this somewhat later Cretaceous, really transform faulting that sort of cuts off this older basin shown here in blue. So basically, you have an older rifted margin, non-volcanic rifted margin, but then we quickly get into Demerara, which is a hotspot track. So you can see this is the track. It goes all the way across to the Guinea Plateau over in West Africa. So very rapid transition from a volcanic margin to non-volcanic and then back to non-volcanic because of this hotspot track. And you see the same thing in Senegal, volcanic margin. You go to Mauritania, it's a non-volcanic margin. But the importance of understanding Guyana has been such a gold mine. This was the initial discovery, 2016. Now it's up to, I think it's like 16 billion barrels of oil. So it's a huge oil find, and I'll go over that system in a minute. So like I mentioned, we use gravity magnetic to define the COB. So here it's interesting. There's the Guyana, we call it the Guyana Rift. There's the Nickerie and the Como line, which other people have described. So we have these parallel, almost like railroad track rifts. In our view, this is an orthogonally rifted margin. Most people call this a transform margin, but it just doesn't make a lot of sense how you could form these twin rifts in that orientation. And notice they track all the way down into Brazil. So it's not like a local feature. These are pretty much all up and down the coast of South America. But again, here's the Demerara Plateau, which is this sort of localized hotspot track. And this would be the non-volcanic. That's non-volcanic. Just a couple of cross sections. This would be the older ocean cross out here. Ranger Seamount here. And then the Demerara itself is this sort of massive thing that's slightly folded by the shearing that happened along called the Demerara fracture zone, which is here. So what is the hydrocarbon system? It's quite simple, really, and it's something that you can apply to many areas of the Atlantic. So basically, you've got Conjay Formation, Upper Cretaceous source rock. You've got Upper Cretaceous fan on top of the Conjay, and then it's sealed by the Paleocene. So it's a big stratigraphic trap, and that's why it runs in a linear fashion along the margin. Pretty deep water, fairly sizable overburden. So that's it. I mean, and that's the model we're using in other places like Uruguay. I mean, Uruguay has almost exactly the same stratigraphy and exactly the same well, it's a little bit more overburden, but it looks very similar to this. So what are some of the important things as far as the basin modeling? One is ocean cross. Where is your COB? And that's important because the rifted continental crust is radiogenic. In other words, the rocks in the rifted continental crust have a radioactive producing heat. So this tends to be a lot warmer than this old oceanic crust out here. Notice where the discoveries are occurring. They're right at the edge of the rifted continental margin. You go from Guyana, non-volcanic, mainly oil fields, and then you start getting into gas fields as you go down into Suriname. Notice the basement here starts to change too because of the hotspot track. But again, a very simple system, Conjay source, submarine fan, late Cretaceous, and then your Paleogene seal. And so you're trapping everything below that seal. And this just shows you have a lot more radiogenic heat production under this continental crust, the necking zone, than you do out on this oceanic crust. So I mentioned, all these inputs, which are numerous, and it takes a lot of time and effort, but I've just listed them here. All of this data, trying to get at the crustal structure, the thermal inputs, bottom hole temperatures, the geochemical inputs, and then you sort of crank it through this sort of AI-based model, and it's starting to give you results, and you can kind of go back through the thing and try to improve it. And you basically get predictive maps of what's called standard thermal stress. So, and this is, well, I'll show you in the next slide. So this is the output of Excalibur, so for Guyana. So you can see this is the Miracle Mile. You can see this trend along here, that sort of circle. So oil fields gets into some gas fields here. The red would be predictive for gas. The green is predictive for oil. So you can see there's a lot of area over in Suriname on the Demerara Plateau, which looks to be prospective based on our model. But notice this is a Santonian 84 million year source rock. This is the Albion 100 million year. So this would be an older source rock. It's more deeply buried. So you have larger areas of gas shown here. Okay, so that's Guyana, and we're refining that model. We're pretty much done with that part, but we want to do the same approach to Equatorial Guinea, or Equatorial Brazil, sorry, along here. And I'll talk about that very quickly. So again, COB is the white line. And notice most of these previous oil discoveries have been within the continent area, but I'll show you in a minute, it's not necessarily true that there's no oil out on the ocean crust, and we have some examples of that. But this is work by Jose Gorosabal using a combination of Petrobras, GeoPost, and other data. But it shows, you remember when I talked about the early transform margin and the transgression during this sort of Aptian-Albian period, this would be when that valley was opening up between North America and Africa. And this is really the top quality source rocks. So right in this sort of interval between the rifts, which you can see down here, and this sort of sag, which you can see up here, which forms these kind of bright reflectors. So this would be the top Aptian. So this is really the sweet spot in this area for source rocks. And Jose has compiled many logs, so this is all very tightly constrained oil show information. Okay, and just another view of that. Notice these very bright reflectors here. This is the characteristic source rock signature. Notice it's at the very top of the rift or in the sag immediately above the rift. And these have the highest organic values are right at that interval there. So we really have nailed down the source rock in this area. And there's quite a bit of exploration going on now, mainly Petrobras, Murphy Oil, Shell, and yeah, all looking out here in the deep water. Okay, so I'm going to wrap up here with the Equatorial West Africa hydrocarbon trend. So this is work Jamoki has been working on, and also Jose is also doing a study down here in Equatorial Guinea. So gravity work, again, COB is the white line, and this has changed a little bit, but it's basically through here. Notice it goes under the Niger Delta. So that would mean prospective areas up to the line or even out beyond this line in certain areas. These are the known hydrocarbons: green, oil, yellow, mixed, red, gas. You can see they kind of peter out. It's a little bit scattered along here. It's a very narrow margin. More wells, more success down here in Gabon and Equatorial Guinea. So it's really crucial to understanding the COB and how that interacts with the delta. So this is a map that Jamoki has made using magnetic data just to show a few trends. So here's this white line would represent the COB being proposed here. These kind of features here would be in the Benue Trough. You can see the ocean crust out here. And then the delta is this sort of big circular area that covers everything. So she's also used some ion data, which is shown here, an example, to try to better map out this big depot center related to the Niger Delta, because beneath this is probably prospective source rock. But notice here she's got some 1D models, 1, 2, 3, 4. So 1 is prospective, it's in the oil window. 2 is in the gas window, it's a little bit deeper buried. 3 is out here. Notice that's in the oil window, even though this is on ocean crust. And then 4 is out here also. It's prospective. So there's a very wide zone here in the deep water, which all looks prospective based on her work. And then I'll wrap up with Equatorial Guinea. This is the work that Jose's been doing. Kind of a steep sort of transform type margin, but it's got rifts, in here, a sag. It's got a little bit of salt that's gotten up this far north, and then a pretty heavy overburden. So Jose has done some modeling, and it does appear that some of these Cretaceous source rocks out on ocean crust are mature. So this would be an example where you could have a petroleum system on oceanic crust. Okay, so I'll wrap up here. Just a few conclusions. I think everyone here now fully understands these different terms that I've used. Correlating the rifted passive margin with hydrocarbons, low and high tapered margins. The low taper is the orthogonal rifted ones. High taper are the short stubby ones are strike slip, and then the kind of drawn out tapered ones are the orthogonally rifted. And then just the impact of non-volcanic versus volcanic on exploration. As we know from Namibia, volcanic margins are now in play for these big discoveries. Some of the oblique rifts in equatorial Brazil, West Africa, related to the transform motion. And then I talked a little bit about Campos Santos, the very deep water there, and then some of the trends that we see in the Niger Delta and equatorial West Africa. With that, I'll wrap it up. I'm happy to answer any questions.
Thank you very much, and right on time. I'm sure we've all learned one thing or the other. Professor of Geology, you must have gone through like Geo 7356 today. But it is very educative, and I'm sure we've all learned something. So, Mr. Sapere, I will call on you to do a quick wrap up before we take questions.
Yeah, thanks a lot, Jumoke, and many thanks, Professor Paul Mann, for this very insightful presentation on a really very interesting topic. So just to give a little bit of a summary, so I've taken quite a lot of notes, so clearly it's always a great sign. Some of the emphases which you have shared are really the focus on passive margins. It's obviously a good environment for hydrocarbon accumulation, as most hydrocarbons are found there, as they have not been they've not been recently disturbed by any recent deformations. So passive margins and continental rift margins, they house about 65% of discoveries known to date. So which underlines what you mentioned earlier. You highlighted the clear transition in exploration from land to more deep offshore and even ultra deep offshore. You focused a lot on non-volcanic versus volcanic margins. You stated that volcanic margins, they house the main discoveries to date because of the main volcanic materials they completely fill the subsurface spaces in those volcanic margins. But there are some exceptions, like Namibia, as you did mention. So it's good to understand closely each basin as we continue to prospect for further hydrocarbon accumulations in different basins. You also talked about the importance of the knowledge of the basin evolution. In fact, this is, for me, it was a key point. The volcanic activities, the fault patterns, the orientations of the rifting, And the fact that sometimes a non-volcanic basin at a different geological time could evolve to become a volcanic and non-volcanic basin. So understanding this evolution is key as well to be able to know if these basins could house potential hydrocarbons. So that was a good learning point as well for us. So then you talked about the where is the COB? There's a clear correlation and a link between the known hydrocarbon accumulations. You showed many examples like offshore Brazil, Santos Campos basin, and where the COB, there is a clear relationship between some of the discoveries and fields and the location of the COB. Not all the time, but could help you to be able to understand a little bit more where hydrocarbons are housed. And then, of course, Niger Delta, where some of the discovery and producing fields as well are orientated just east of the COB. The importance of basin modeling as well. It is always a great investment for us to be able to model all the tectonostratigraphy, structural inputs, have all the thermal inputs, to be able to understand the movement of hydrocarbon and understand the potentials of our basins being key to unlocking deepwater exploration. So thanks a lot. I have learned quite a lot. So at this stage, I would like to now pass it back to Jumoke to moderate the Q&A session.
Thank you, Mr. Siapere. For me, a key takeaway was the fact that we have all this information. What do we do with it? So putting everything into an integrated basin modeling that is meant to be for predictive purpose is a big deal. And to be able to do that, I'm sure there are key enablers that Professor Mann can, advise on how that can happen. While we are waiting on questions, Dr. Mann, I have a question for you about, you've mentioned some hotspots for deepwater exploration in the future. So what, in your opinion, are the key enablers you think should be in place for us to be able to effectively exploit these deepwater frontiers?
You mean in terms of what area is most promising? Or
Yes.
well, I mean, I think the good news with this whole presentation is that everywhere is in play. I mean, if you think about it, how many of these situations are there in the world? There are a lot in the Atlantic. There are a lot of these, where you've got a rifted lower part and you've got a sag and then you've got a cover. And you have these transgressions that produce the high quality source rock. So I guess the message here is that this happened over huge areas. It wasn't restricted to one small area. It happened over Brazil, West Africa, all these places. So the good news, I think, is that there's probably a lot more oil and gas out there than people might suspect, given that these events affected everywhere. Of course, maybe there's too much overburden, maybe there's not enough overburden. I mean, there could be some factors like that, but overall, this is a good news, optimism message.
All right. Thank you for that response. So,
well, before I want to go, I just wanted to point out, if anybody would like any of these reprints, I can't post these online because of the copyright restriction, but if anybody would be interested in these, I could send you these PDFs, right? And this out of this volume called Deepwater Sedimentary System, published in 2022, edited by John Rothstein. But these two papers are what we contributed to this volume. And this is more of just a minor little thing about the terminology of passive margins. But if anybody's interested, just send me an email and I could send you these PDFs. But like I said, I can't put these online, so that's the problem.
okay, thank you for that. So there's a comment and I guess also a question. I'm guessing this is a student. So excellent and insightful presentation, Professor Mann. This is coming from Elijah. He asked about recording of this presentation. Yes, it's recorded. But you also heard Professor Mann say if you need something specific, directly contact him. And also, secondly, he said he was wondering if there are available spaces in your lab for MSc students. He is a recent first-class graduate of geology with interest in reservoir characterization and modeling. We love first-class students. He wants to know if there are opportunities for the likes of.
Well, I mean, I guess there are probably opportunities if you can self-fund and either through a company or something like that. We have a guy coming from Petrobras in a few months who's completely funded by Petrobras. So that's more likely than us supporting you because like we just have 5 sponsors and we have a group of 10 people. So we're somewhat limited in the RAs that we can offer people. So but I think if you are with a company and that company is interested in this type of work, then you might ask them if could they support you for a master's or even a PhD. So
Thank you for that response. We'll move on to the next question. Arancel Leveld asked, what are your thoughts on deepwater systems where the depositional setting becomes very flat in terms of structures in the abyssal plain? Have you worked on such systems and have they proven?
well, yeah, I mean, you're right. Passive margin, there's really no structure. Or I mean, these sections here in Guyana are vertically exaggerated, but these are pretty much flat. Everything is flat. There's maybe a few faults up dip, gravitational fault, but down here there's zero structure. So what does that mean? That means all of these traps are stratigraphic. They're onlaps that are sealed by shale units. So structure in this world doesn't matter. It doesn't make any difference. People are so used to exploring, looking for anticlines and that sort of thing. But this is a whole different system. Over here, we're looking for stratigraphic traps, and big. The advantage of the stratigraphic trap, it can be huge, like we've seen in Guyana. So these are much bigger structures. You just need, the right combination of a source, a reservoir, and a seal. So
Yeah.
so faults are not that important in this system.
Okay, thank you very much. So the next question is from Chidozie. How is this concept going to help in hydrocarbon exploration in the Benue Trough, Nigeria? Chidozie is from the University of Port Harcourt.
Well, the Benue Trough, I mean, would be an example of one of those on-land areas that's pretty mature. This sort of delta area or going up into the valley there. So what I'm talking about in this talk is more of a whole different system, possibly different source rocks, definitely, different overlying sedimentary section. I mean, this would be sort of an on-land sort of rift setting with some reactivation, whereas this could be a completely undeformed area, maybe deformed by gravity, but no sort of tectonic faults. So it's really very different, I think. It would be sort of comparing Texas to the Gulf of Mexico in terms of geology.
Absolutely. Well said, Dr. Mann. Like he said, it's a different system, and for the Benue Trough, it's very matured based on the work out there in the journals that a lot of researchers have done. Basic modeling in the Benue Trough shows that oil has been produced, generated and expelled in the past. We could see oil seeps in some of the basins, like Anambra Basin, in the Benue Trough. So yes, but it's a different concept entirely. But the good news is there is a trend that we know based on the Cretaceous source rock in the Benue Trough that extends underneath the Niger Delta, and you probably can find some of those at the fringes of the Delta. And if you have the right data following that trend, we saw the Ugu and Aji fields. They've drilled similar source rock hydrocarbon based on similar source rock like the Bay nature of Cretaceous. Awesome. So I think we are right on time. There are no more questions. Once again, we want to thank Dr. Mann for his time, and it's been a lovely and interesting discussion. So I'll call on Cynthia now for, oh, oops. There is one last question that just came in as I was talking. So I'm just going to take that one, Dr. Emmanuel Madua-William, and we'll move on. That will be the last question. What advancements in autonomous underwater vehicle AUV technology are most critical for enhancing deepwater exploration capabilities beyond current depth and duration limits?
Underwater vehicles probably are not that important for exploration. I mean, what's important for exploration would be geophysical methods. So ship-based 3D seismic, very advanced processing of the seismic data. I think the underwater vehicles might be more the operation. In other words, when you drill a deep water well, you do need on site, bottom vehicles for the drilling process, but I don't think that's really that important for the exploration process.
Exactly. Yeah. And there are big changes in technology driving deepwater trend, like Dr. Mann said, because they are the ultra deepwater is deeper. You need a different set of technology to be successful and a bit more profitable than shallow water. So advances in AUV might be something, but like Dr. Mann said, it's towards the execution. Thank you once again for answering that very quickly. Let's move on now. Cynthia for announcements.
Hey, good evening, everyone. I will share my screen in a moment. Okay. All right. Yeah, thank you very much, everyone. The announcements for today. Technical business meetings will still be ongoing. We're calling on sponsorship for our monthly business meetings. For further inquiries, please contact Mrs. Olajumoke, Cecilia, the PEF NAPI, or Mr. Lawrence Oswago for sponsorship. We're also calling out for registration for the 2025 NAPI Annual International Conference and Exhibition. The theme is revitalizing the Nigerian petroleum exploration and production strategies for energy security and sustainable development. Sponsorship opportunities exist in different categories, and the early bird registration for this conference will be ending on the 1st of September. Please do take advantage of this opportunity. We're also calling for abstract submissions on the following sub-teams. The deadlines for abstract submission is on the 31st of July. Is on the 1st of September 2025. To submit your abstract, please go to the Sessionize tab accessible on the NAPI portal. NAPI celebrates its Golden Jubilee anniversary this year. The event will be taking place at Eco Hotel and Suites, Lagos, Nigeria, on Thursday, the 14th of August, 2025. This event is strictly by invitation. Please reach out to the Secretariat for more information. We're also calling on members to renew their dues. Kindly pay into the account on the slides. 1005158 UBA NAPE, or for further inquiries, please contact my ya@nape.org.ng. Student membership still remains 2,000 naira. Active membership 12,000, associate 12,000, and corporate members 50,000 each. We're also calling on geoscience professionals in North America to join the chapter to receive timely updates on upcoming events, build your network, and also get more information on events and hangouts happening in your area. And the chapter uses this opportunity to thank all members that were able to attend our GeoPlay Exploration Games Nights that took place last week. And we're also calling on you to join us and get timely information on all our upcoming events. Thank you.
All right, thank you, Cynthia. And we are right on time. We will have closing remarks from the chapter coordinator, Ademola Lanisa.
Okay, thank you very much. Please confirm you can hear me.
Yes, we can.
Yes, thank you. Yeah, it's been an exciting webinar, very informative. Special thanks to Professor Mann. Yeah, it was quite, intriguing. It was also very informative and thought-provoking. Yeah, looking at all the systems that you talked about, passive and active margins, and the new ideas and concepts that you proposed with respect to frontier areas. We want to thank you very much for this very interesting talk. And yeah, also we want to express our thanks to the research team, to the CBTA team, and all who contributed to the materials that you shared with us. I'm sure this engagement will continue even outside of this presentation. Also, we want to thank the NAPI president, Mr. John Bosco, FNAPI, and our president-elect, Mrs. Olajumoke, for being here. Yeah, I know it's past midnight now in Nigeria. Thank you so much for connecting and being part of this. And also to all our members, for those who connected from Nigeria, thank you for waiting and being part of this. And for those who are here as well, yeah, thank you for being part of this as well. And as mentioned earlier, please watch the social media space, especially LinkedIn, and also your emails for upcoming activities and all the exciting things that we've planned for the rest of the year. So once again, thank you everyone, and enjoy the rest of your evening.
Thank you, Demola. And it's a wrap, everyone. Thank you for joining us. Stay tuned for third quarter presentation. We'll send details out, like Demola said. Have a nice evening, everyone.
Okay, thank you guys.
Thank you.